All right, so we're going to cover a few different things today. The first thing will be implicit differentiation. So I'll talk about that a little bit, and then derivative of log and ln. So the first thing that we need to know is using a particular notation in order to kind of apply that within some of our other stuff that we're going to be doing. We also need this implicit differentiation when we do when we prove the derivatives of the logarithmic functions, which is why we kind of need to know how to do it. Derek, can you close the back door? Okay, so we're going to kind of learn how we can split up a function. So this actually relates directly back to chain rule, but we're going to learn how we can split up a function and figure out how we can take the derivative of pieces of it, kind of. That's kind of the goal, in order to make our derivative maybe a little bit simpler. So what we do is we're basically going to set the inside of this function equal to u, and then replacing 5 plus 2x with u, we have y is equal to u to the 10. Okay, so we're just subbing in u here. And when we calculate the derivative with respect to x, now in this function here, if we're trying to calculate the derivative with respect to x, we have to first calculate the derivative with respect to u, and then we will find the derivative of u with respect to x in that second function. So here's the idea. The idea is that if we split this into two functions, one with respect to u and then u with respect to x, dy over dx is going to be equal to dy du, so the derivative of the y function with respect to u, times the derivative of the u function with respect to x. So you can kind of see here that these are like basically canceling each other out. So it's still equal to dy over dx. Okay, so the thought is that if we can split these up into their own functions and find their derivatives and then just use this, it makes things a little bit simpler as far as chain rule. And it also kind of grounds the idea of chain rule as well. So dy over du, so if we're using the function y equals u to the 10, what's the derivative of this function with respect to u? So just power rule. So that would be, I think you're doing 10 to the u, Grayston. We're doing u to the 10. So it would be 10 u to the 9. Okay, and then if we look at our second function, which is u and x, I want to find du over dx. So using this function here, what is the derivative of the function u with respect to x? It's just 2. Okay, so now that we have these two pieces here, we can actually use this idea. So I found dy over du, it's 10 u to the 9. And I found du over dx, it's just 2. So that actually gives us 20 u to the 9. And I still want to actually know the derivative of this original function. So we're actually just going to sub back in the value of u, which is going to give us 5 plus 2, or 5 minus 2x rather, to the exponent 9 with a coefficient of 20. Okay, so we're subbing back in this equation here.
Why can't you just use chain rule?
So we can definitely use chain rule, but this notation idea kind of grounds what we're going to do next. So yeah, we certainly know, like, of course we can use chain rule, but this notation sometimes makes it a little bit easier for us to take pieces of the function in more complex derivatives. It also basically allows us to do this next part, which is called implicit differentiation.
Why is it minus?
Oh yeah, it's plus, sorry. Thanks. Okay, so certainly we already know how to take the derivative of something like this, but we just haven't done it in this particular notation before. Okay, so the reason why we need this is for what we call implicit differentiation. So basically all of the functions that we've been differentiating so far are essentially y equals and then everything to do with x, or everything to do with a single variable. This is called explicit differentiation, or not necessarily explicit differentiation, but differentiation of a function that is explicitly arranged so that y can be equal to something in terms of x, okay? So we call those explicit functions. Now, there are some functions that are called implicit functions, which could be very difficult to isolate in terms of y, or could potentially be almost impossible to isolate in terms of y. So something like a circle, x squared plus y squared equals 16, you actually can't isolate this in terms of one single function. When we isolate y in this function, we actually get 16 minus x squared, and then we would have to do the positive and negative square root of this function to get both sides of our circle. This is actually two different functions. This is the positive root of 16 minus x squared and the negative root of 16 minus x squared. So there's no way that I can actually express y isolated in terms of a single function, which in this case is not like completely horrible, but in other cases there won't be a way that I can explicitly isolate for y, which is why we need something called implicit differentiation. So we're going to use this idea that we used above, and we're going to make sure that we can, if we're differentiating with respect to x, that we also have a method that if y is inside that function, we can also differentiate that piece of the function. Okay? So basically what this is saying that you have to do is if you're differentiating with respect to x, a function that has y inside of it, we have to take the derivative of the y function, and we also have to multiply by dy over dx in order to get the full derivative. So I'll show you what I mean in an actual example here. Let's use the example that I presented to you above, x squared plus y squared equals 16. So when we do this function, we're differentiating with respect to x, so dy over dx. That's kind of what we're trying to find. So I'm going to find the derivative of x squared as usual. So what's the derivative of x squared? Okay, it's 2x. And then also we're going to find the derivative of y squared, kind of similar to how we would apply power rule. So I know I need to bring down the exponent and subtract 1, so we get 2y. But I also, so that's this part of what we were talking about. So basic derivative rule, but we also need to differentiate y with respect to x, which is basically just dy over dx. So we are going to kind of apply like a little bit of a chain rule type thing where we have to multiply by the derivative of the inside. Well, the derivative of y is dy over dx. It's the derivative of y with respect to x. And derivative of 16? 0. Yeah, so you can put y prime, or the other notation is, of course, dy over dx. So I want to isolate for dy over dx so that I know what this function's derivative is with respect to x. So that's the goal. We're going to differentiate, we're going to isolate for dy over dx. We'll get negative 2x. We'll divide out that 2y. And we'll just reduce those 2's there. So we know the derivative of this function now with respect to x is negative x over y. Okay, so basically we're going to do this anytime that it would be very difficult for us to isolate for y, or essentially impossible for us to isolate for y, a single y. Okay, if you tried to isolate for a single y here, of course there's multiple y's with multiple different exponents, so that's going to be very difficult for us to, or like basically impossible for us to do. That's why we need implicit differentiation. You don't have to use dy over dx, you can just say times y prime. That's what you'll see in most of my solutions, just for simplicity's sake. Okay, so we're going to apply the regular derivative rules, but remember anytime you use the derivative rules with y, you also have to multiply by y prime, or dy over dx. So here, so same idea of what we did here, we're going to bring down the 2, subtract 1 from the exponent, and then kind of apply like a chain rule thing here where we also have to multiply by the derivative of y with respect to x, or in other words, y prime. Okay? The derivative of x with respect to x we know is just 1, right? So technically we are doing that when we do power rule with x, but there's no need for us to constantly multiply by 1. when we do that. So here, we're going to use power rule. And then, of course, we know if we were to differentiate like with chain rule, the derivative of x is just 1. So we don't have to do that, right? That's what I'm talking about. Okay, so same thing over here. Apply power rule, subtract 1 from the exponent, and then apply chain rule. So you have to multiply by the derivative of y. Derivative of 6 is 0, and then the derivative of 3y. So what's the derivative of 3x? It's 3. So the derivative of 3y is 3 times the derivative of y. So this will be 3y prime. Okay, so we have multiple y primes in here. It's not as easy as just isolating for dy over dx or y prime like in part A. So your goal here, let's get everything with a y prime to one side, everything without a y prime to the other side. So I'm going to leave this guy, and we'll also leave this one. And we're going to bring this to the opposite side, so we'll get negative 3y prime. And then this guy I'm going to bring over here. Okay, if I want a single y prime here, I'm going to have to common factor a y prime from each of these terms now. So we're going to take out that y prime so that we have just a single y prime, or dy over dx if you'd like to use that notation. And now we can get y prime by itself by just dividing this bracket out. Okay, so this is what you should get. You can also, if you're wanting to use dy over dx notation, you can do that as well. So dy over dx, or you need to put the y primes in your equation, okay? So that's what our derivative should be equal to. Can I clarify anything here? Keely.
Wait, so basically you just, like, whenever you take the derivative of y, you multiply it by y prime so that you can isolate the one.
Yep. Yep. Okay, we are differentiating with respect to x. So if we're differentiating a different variable with respect to x, we have to say like d whatever the variable is over dx. So in this case, when we multiply by y prime, we're saying derivative of y with respect to x.
Where does the equation come from, though? Like, I just don't understand, like,
What do you mean?
like the original, like, I don't know, I don't understand. how
Like
it's-
this?
No, like, the other page.
This?
Yeah.
So basically this is saying like basically what I just said to Kaylee. So this is saying if you differentiate any variable, it doesn't necessarily have to be y, but if you differentiate any variable with respect to a different variable, you have to apply the derivative rule. So you'll apply the derivative rule of dy, right? And so this is essentially just saying take the derivative of whatever the function is with respect to y. And then you also have to multiply by the derivative of that variable with respect to x. So it's basically kind of coming from what we talked about up here. So if I do dy over dx, I can split this into multiple parts and just multiply them. So essentially this is telling us we're taking the derivative of the function that has the pieces of y in it with respect to itself. So that's how we're getting like these pieces, just regular derivative rules. But then you also, in order to get the derivative with respect to x, you have to multiply by the derivative of the variable with respect to x. So in this case, it's dy over dx, or y prime.
So when do you know when to multiply by?
So anytime you are taking the derivative of a function with respect to x and you have other variables in there, you will have to multiply by y prime, or in other words, the derivative of y with respect to x, dy over dx. So here's the idea. When we simplified, when we were talking about this up here, dy over du technically, like, and then du over dx is really just dy over d.
Yeah.
x, right? Agreed?
Yeah, I just don't.
So the same thing is basically happening here. So if we're saying we're taking the derivative of the function with respect to x, and that function has y's inside of it, we're basically just saying this is what it's equal to, right? So it's saying take the derivative of the y parts with respect to y. So apply the derivative rule, and then you have to multiply by dy over dx to get the derivative of that piece with respect to x.
Okay.
Does that make a little bit more sense where that formula comes from? Okay.
That's just for the y's though, right?
That's just for the y's, yeah. We can differentiate all the stuff with respect to x as we have always been doing.
So when you did the 3x squared, how can you accept it? Technically, it's a good chain rule, like if you want, like works up front and even like mentioned.
Yeah, so I'm just saying basically like when we do the derivative of something like 3x squared, or x cubed, we technically are multiplying by the derivative of the inside when we do this, right? We're always applying chain rule. We just do like the power rule, and then if we were to multiply by the derivative of the inside, what's the derivative of x? It's just 1. So really we are doing that every time that we apply power rule. So I'm just kind of trying to make a point that like we're doing that anyways, and that's kind of where this y prime piece comes from when we do that with y's rather than x's. But yeah, basically you're differentiating all the x's with respect to x as usual. Okay. So we're going to use this idea of implicit differentiation to figure out what the derivatives of logarithms are. So the very first thing, in order to prove the log of any base to an x, we're actually going to switch this into inverse form. So we're going to switch it into exponential form. Can someone switch this into exponential form for me? Gabby? Yeah, you're going too complex with this. So it's a to the power y equals x when we switch into exponential form. All right, so you can see now why we need implicit differentiation, because I'm differentiating something where y is in the exponent in order to prove this logarithm. So if I take the derivative of any base to an exponent, what do we know about exponential functions? What's like the derivative of b to the x? Okay, so it's going to be, we'll get back this piece, right? And then we have to multiply by the derivative of the base. And I also have to multiply by the derivative of the exponent with respect to x here. So what's the derivative of the exponent with respect to x? It's dy over dx, or y prime, right? Okay, so kind of like chain rule again here. And then derivative of x is 1 with respect to x, yeah. Okay, so your goal here, we want to isolate for dy over dx. So we're going to divide this out. And what do we know about a to the exponent y? Look through the function. Through the steps here. It equals x. So I know that this actually equals x. So my derivative of this function is actually going to be equal to 1 over x times the ln of the base of the logarithm. So if you look at what your base is here, you're always going to have the ln of that base in the denominator. Essay?
So, as long as y is anywhere in the function, it's going to be multiplied by the y prime.
Yep. Okay, so this is the basic proof of any logarithm with any base. So a represents any possible base that we could have to x. So we will get 1 over what's inside the logarithm times the ln of the base. So if you have a little bit more of a complex function, here's kind of what you can use. So you're going to use chain rule in order to do this. So you're going to get any constant multiple will be copied into the denominator. You will do the function that's inside log, copy that into the denominator. You'll multiply that by the ln of the base, just like we saw here, ln of a. And then you will, if you have a function, anything other than just a single x inside your logarithm, you're going to place the derivative of that function in the numerator, okay? That's kind of the shortcut explanation. So in English, it's kind of written for you over here. So constant multiple, and also the derivative of the function inside the logarithm into the numerator, over the function inside the logarithm, just as it is, times the ln of the base of the logarithm, okay? So we're gonna practice it a little bit. I know it seems complex right now, but you'll get the hang of it. You wanna do it? Go ahead.
So it's -1, you have negative c value,
Yep,
over 2x minus 1,
yep,
ln 4
mm-hmm,
times 2, or is
times
times 2.
2. Okay, so this is what Grayston did. So think of this as like if it's -1. The derivative of 1 is just 0, so that will be gone. Copy the constant multiple into the numerator. Copy the piece inside the logarithm into the denominator. Multiply by the ln of the base in the denominator. And then up here, this is the derivative of the function inside the logarithm. So the derivative of 2x minus 1. That goes into the numerator. So if we simplify this, just like an extra little step here, we're just going to gather these two guys on the top. We'll get -2 over 2x minus 1 times the ln of 4. Okay, what we could potentially do here, I've also done this in like a previous worksheet, is we could, because this is the ln of 4, we could express this as 2 to the exponent 2. And what this allows us to do is we can actually bring down this exponent as a multiple. We know anytime we have the log of something to an exponent, we can use power rule. And what this actually allows us to do here is reduce the 2 on top with the 2 on bottom. If you're looking like for a, you might see me do this in some questions, so I guess like the idea is behind me showing you this is that we can technically simplify these a little bit more in some cases. If you don't do it, it's not going to be a huge deal, but if you happen to see something that maybe doesn't line up with the answer that you got, I probably simplified it a bit further. So just so you know, with your simplifying, technically it would be ideal if it's fully simplified, but I won't be too picky over this one. We'll give someone else a chance. Are there any questions on this before we move forward? Anything at all? We're all okay? Okay, does someone want to try the next one? Okay, Grayston, go for it.
2 over 1 is x squared. There's another value in the bottom, which is x value.
What?
I got the top is 4x.
Okay. So what did you multiply by here? How about ln of e? What's the base of this logarithm? So guys, remember, ln is the log with base e. So what should I be multiplying by technically in the denominator here? Or ln e, right? Ln of the base.
But that's just 1.
Yeah, it is just 1, but I want to make sure that you guys know that. So, and then you're multiplying by the derivative of this inside function. So the derivative of 1 plus x squared, that's 2x. Okay, so you will notice anytime you are taking the derivative of a function with ln, so the ln is still a logarithm, it's just ln with base e. What always will end up happening here is that the ln e is actually going to appear in your denominator, and that will always equal 1. So we can simplify for this particular function. When you're doing the derivative of any logarithm that has like any ln basically, you don't have to do the ln of e, obviously. I don't really need to see that part. It's always just going to equal 1. So what you'll end up getting is 1, or the constant multiple, over the inside function, so whatever is inside the logarithm, and then multiply your constant multiple in the numerator by the derivative of the inside function. Okay? I don't need to see this part. That's always going to equal 1 for this particular case. Okay, so that's basically what I've just summarized here for you. The derivative, because ln is just log with base e, you will always see that you'll get ln of e in the denominator when you do the ln of the base. So the derivative of ln x is basically just 1 over x. And then if you have a more complex function, you will copy the constant multiple into the numerator, copy the function inside ln in the denominator, and multiply by the derivative of the inside function in the numerator. Okay, so there's like a shortcut explanation for you there. Any questions on this second one here? Yep. Yeah, so I don't need to see that. If you want to put it just to feel happy, then you can. But you need to replace it with 1 anyway, so you'll have to simplify it. Yeah. Okay, so no further questions? We're all good? Okay.